somewhere out past the orbit of Jupiter, moving faster than almost anything the Sun has ever pulled into its gravity. There is a rock. Or maybe it isn't quite a rock. Maybe it's something closer to a fossil, a chunk of frozen chemistry that has been drifting through the emptiness between stars since before our own sun had finished forming. We call it 3I/Atlas. And if you want to understand why astronomers dropped what they were doing the moment they got a good look at it, you have to understand one simple fact first. This object did not come from here. It didn't form in our solar system. It wasn't nudged out of the asteroid belt or flung in from the Oort cloud. It arrived from somewhere else entirely. Another star system, another disk of dust and ice, another corner of the galaxy. And it has been traveling, alone in the dark, for longer than human civilization has existed. Longer, possibly, than our entire species has existed. Some estimates put its age at 3 to 11 billion years. Let that sit for a second. Our solar system is 4.5 billion years old. This visitor might be older than the Sun itself. It is only the third interstellar object we have ever confirmed. The first was Oumuamua, back in 2017. A strange, elongated thing that tumbled through our neighborhood and left scientists arguing for years about what it actually was. The second was Borisov in 2019, a genuine comet with a visible tail, behaving more or less the way comets are supposed to behave. And now, in the summer of 2025, came the third 3I/Atlas, spotted by a network of telescopes literally built to watch the sky for exactly this kind of thing. Asteroids, comets, anything that might be worth a second look, or in the worst-case scenario, anything on a collision course with Earth. Nobody expected trouble from this one. The path was calculated almost immediately, and it became clear that 3I/Atlas poses no threat to our planet. It will swing through the inner solar system, loop around the Sun, and head back out into interstellar space, never to return. This is a one-time visit, a single flyby, and that is precisely why every major telescope humanity has pointed at the sky, from ground-based giants to the crown jewel of modern astronomy, the James Webb Space Telescope, turned its attention toward this small, unassuming traveler while it still had the chance. Because here is the thing about interstellar objects. They are messengers. They carry, frozen inside them, the chemical fingerprint of the place they were born. A place we will almost certainly never visit, orbiting a star we may never even identify. When ice from another solar system starts to sublimate in front of our instruments, we are not just watching a comet warm up. We are reading a letter that was sealed billions of years ago, on the far side of the galaxy, and mailed to us by pure cosmic accident. And when scientists finally opened that letter, they found something they were not expecting. Let's start with the basics because the setup matters. A comet, in the simplest possible terms, is a dirty snowball, ancient ice mixed with dust and rock, left over from the earliest days of a planetary system. As a comet gets closer to a star, sunlight begins to heat its surface. The ice doesn't melt into liquid the way ice does here on a summer sidewalk. Instead, it sublimates, turning directly from solid to gas. That gas erupts outward, dragging dust along with it, and forms a glowing cloud around the comet's icy core called a coma. Push that gas and dust back with the pressure of sunlight and the solar wind, and you get the tail, the thing most people picture when they hear the word comet. In our own solar system, comets are made mostly of water ice with smaller amounts of carbon dioxide, carbon monoxide, and a scattering of other frozen compounds. Water dominates. That is the pattern astronomers have observed again and again in comet after comet, for as long as we've had the instruments to check. It's not just a coincidence, it reflects the conditions under which our solar system's comets formed, out in the cold, water-rich regions of the early solar disk. So when the James Webb Space Telescope turned its infrared eye toward 3I/Atlas and began analyzing the light coming from its coma, astronomers expected to see the familiar signature. Some water, some carbon dioxide. Business as usual, just from a much older and much more distant point of origin. That is not what they found. Using an instrument called NIRSpec, a spectrograph capable of splitting incoming light into its component wavelengths and identifying the chemical fingerprints hidden inside, researchers discovered that 3I/Atlas's coma is absolutely dominated by carbon dioxide. Not a minor ingredient, not a side note, the main event. Water is present too, along with carbon monoxide and a tentative trace of carbonyl sulfide, but water is playing a supporting role in a story where carbon dioxide has taken the lead. Here's where it gets genuinely strange. When researchers measured the ratio of carbon dioxide to water in the coma, they found something in the range of 7 to 8 parts carbon dioxide for every 1 part water. To put that in perspective, for most comets we've ever studied at similar distances from the Sun, water is the dominant volatile, not carbon dioxide. A ratio this high is not just unusual statistically, it sits somewhere around 4 to 6 standard deviations away from what you'd expect based on the entire population of comets we've measured before. In plain language, if comet chemistry were a bell curve, 3I/Atlas isn't sitting near the edge of that curve. It's sitting so far out in the tail that it barely belongs on the same chart. Now, scientists being scientists, the first instinct wasn't to panic or to start whispering about aliens. The first instinct was to ask, what could actually cause this? And there are a few compelling answers, each of them fascinating in its own right. One possibility is age and exposure. 3I/Atlas has spent an almost incomprehensible amount of time drifting through interstellar space, potentially billions of years, bombarded the entire time by cosmic rays, high-energy particles zipping through the galaxy at close to the speed of light. Over that kind of timescale, cosmic ray bombardment can chemically reprocess the outer layers of an icy body, essentially cooking a crust of altered material onto its surface. Some researchers have suggested this comet may have developed a kind of cooked shell during its long journey, an outer layer enriched in carbon dioxide ice, formed and reformed by the slow, relentless radiation of deep space. When the comet finally approached our Sun and began to warm, it was that CO2-rich outer shell that vaporized first and dominated the coma we now observe. Another possibility reaches back even further to the very beginning, to the environment in which 3I/Atlas originally formed. Every planetary disk around every young star has zones at different distances where different ices can condense, depending on temperature. There's a frost line for water, and further out, a colder zone where carbon dioxide ice becomes stable. If 3I/Atlas coalesced from material that formed closer to or within a carbon dioxide-rich zone, perhaps around a star with different chemistry than our own Sun, or under different radiation conditions in its youth, it could have been built from the start with an unusually high proportion of CO2 relative to water ice. There's also a third, deeper possibility that has genuinely reshaped how some scientists think about this object. 3I/Atlas might have formed in a completely different part of the galaxy than most of the comets we're used to studying. Some analyses of its trajectory and estimated age suggest it could have originated in the galaxy's thick disk, an older, more metal-poor stellar population than the one our Sun belongs to. Stars in that population formed under different chemical conditions, with less of the heavier elements that were still being cooked up inside earlier generations of stars. If 3I/Atlas is a relic of that older, chemically leaner environment, its strange composition wouldn't be a fluke, it would be a direct, physical readout of galactic history, a sample of chemistry from a chapter of the Milky Way story that predates almost everything we know. Think about that for a moment. This is not simply a weird comet. This might be a physical time capsule from before the Sun existed, carrying inside it the chemical memory of a completely different neighborhood of the galaxy. One that formed under different rules, seeded by different stars at a different point in cosmic history. And it just happened to wander close enough for us to catch it, point our best instruments at it, and read what it has to say, during the one brief window we'll ever get before it vanishes back into the dark for good. But the carbon dioxide anomaly, as strange as it is, wasn't the only surprise waiting inside 3I/Atlas. There was something else. Something that, in some ways, is even harder to explain. Ground-based telescopes, including the Very Large Telescope in Chile, turned their spectrographs on the comet and picked up something unexpected in its coma. Nickel. Specifically, atomic nickel vapor detected through its characteristic emission lines, the same kind of technique astronomers used to identify elements inside stars, nebulae, and yes, comets, by reading the exact wavelengths of light they emit or absorb. On its own, nickel in a comet isn't shocking. It has been detected before in other comets, including Borisov, the second interstellar visitor. Metals like nickel and iron exist inside comets in tiny quantities, typically locked into more complex, heavier molecules that don't easily vaporize at the temperatures found in the outer solar system. It normally takes a comet getting quite close to the Sun, hot enough to break those molecules apart, before those metals show up as detectable gas in the coma. Here's the part that made scientists sit up. In virtually every comet where nickel has been detected, iron shows up right alongside it in roughly comparable amounts. The two metals are chemical siblings in comet chemistry. Where one goes, the other typically follows. Except in 3I/Atlas, nickel was there, clear and detectable. Iron was not. No matching iron signature could be found alongside it. That's the equivalent of finding footprints from two people who are supposed to always walk together, and only ever seeing one set of prints. It's not that iron is impossible in comets. It's that seeing prominent nickel without any accompanying iron breaks a pattern that has held up across essentially every other comet we've ever measured this way. So what's going on? One leading idea involves a rather elegant, if slightly eerie, piece of chemistry: nickel tetracarbonyl. This is a compound made of a single nickel atom bonded to 4 carbon monoxide molecules, and it happens to be volatile, meaning it can turn into gas and escape from an icy surface at much lower temperatures than pure metallic nickel or typical nickel-bearing minerals would require. If dust grains in the comet's nucleus contain nickel locked up in this kind of compound or something chemically similar, it could sublimate efficiently even out at the relatively cold, distant part of the solar system where 3I/Atlas was first observed, releasing detectable nickel vapor without needing the intense heat that would normally be required. Iron, meanwhile, may simply be locked into far less volatile minerals that stay solid at these temperatures, staying trapped in dust rather than escaping as gas, which would explain why we see one metal glowing in the spectrum and not the other. There's an added twist here, too. As 3I/Atlas has continued its journey around the Sun, later observations suggest that some of these unusual ratios, including the imbalance in nickel relative to iron and other early chemical oddities, have begun trending back toward values that look more typical of solar system comets, at least in certain measurements, as the comet has been more thoroughly heated by its approach to the Sun. That evolution over time is itself valuable evidence, suggesting we caught this ancient traveler in the middle of a transformation, its most exotic and fragile surface chemistry burning off first, layer by layer, as sunlight does what sunlight always does: reveal what's underneath. Put the two discoveries together, an off-the-charts carbon dioxide to water ratio, and a coma glowing with nickel but strangely missing its usual iron partner, and you start to see why 3I/Atlas has become one of the most closely watched objects in the sky. This isn't simply a comet with a couple of quirky readings. It's an object whose chemistry, in more than one independent way, breaks the pattern established by literally every well-studied comet in our own solar system. And there's a reasonable, sober explanation woven through both of these anomalies. This object is old. Genuinely, almost unimaginably old. It has spent an eternity exposed to conditions no solar system comet has ever experienced. The hard vacuum of interstellar space, the endless bath of galactic cosmic rays, temperatures hovering just above absolute zero for spans of time that make human history look like a rounding error. Under that kind of exposure, ice doesn't just sit there, inert and frozen in time. It gets bombarded, rearranged, chemically transformed at the molecular level, in ways scientists are still working to fully understand. Every anomaly we're now cataloging in 3I/Atlas may simply be the signature of deep time itself, etched into frozen chemistry the same way tree rings record decades, or ice cores record ancient climates. There's also the isotope evidence, which deserves its own moment of attention, because it tells a slightly different and reassuring part of the story. When researchers measured the ratio between two forms of carbon, carbon-12 and carbon-13, inside 3I/Atlas, they found values broadly consistent with what we see here on Earth and throughout our own solar system. That might sound like a small, technical detail, but it carries real weight. It suggests that whatever star system this comet formed in, the basic building blocks, the fundamental isotopic ratios of carbon, were forged through the same universal processes of stellar nucleosynthesis that built every other star and planet we know of. In other words, 3I/Atlas is deeply strange in its chemistry and composition, but it is not made of some exotic, physics-defying material. It's built from the same periodic table as everything else in the universe. It's not alien in the science fiction sense. It's alien in the sense that matters more. It's a genuine sample of another corner of our galaxy, chemically foreign to our neighborhood, but built from entirely familiar ingredients. That distinction is worth sitting with for a moment, because it's easy, in an age of algorithm-driven headlines, to let a story like "Interstellar Object Has Weird Chemistry" slide towards something more sensational. And to be fair, this object has attracted its share of speculation, some of it wildly disproportionate to the evidence, including a small number of researchers who raised the possibility, largely as an exercise in ruling things out, that some feature of 3I/Atlas's trajectory or behavior might in principle be explained by artificial origin. That hypothesis was examined, tested against the actual data, the orbit, the composition, the outgassing patterns, the size, and it did not hold up. Every measurement scientists have taken points toward a natural explanation. An old comet, its ice and dust shaped by cosmic ray processing and possibly by exotic formation conditions in a different galactic environment, following a completely unremarkable ballistic path shaped purely by gravity, exactly the way every other comet in history has moved. No srast, no maneuvering, no behavior inconsistent with a natural body responding to sunlight and gravity. Just an old, well-traveled chunk of another solar system, sublimating exactly the way physics says it should, just with a chemical recipe none of us had seen quite like this before. If anything, that natural explanation is more remarkable than a science fiction one would have been. Because what we are looking at, if the leading theories hold up, is direct physical evidence of chemical diversity across our galaxy. Proof that not every planetary system builds its comets out of the same ratio of ice, gas, and dust that ours did. Some corners of the Milky Way, especially older, more metal-poor regions like the galactic thick disk, may cook up planetary building blocks with a genuinely different flavor. We've long suspected, based on theory and on our observations of other star-forming regions, that planetary systems should vary in composition depending on where and when they formed. 3I/Atlas may be the first physical, in-hand confirmation of that idea. Not a model, not a simulation, not starlight filtered through a distant nebula, but an actual object, close enough to sample directly with our own instruments. There is something almost poetic about how we got this chance at all. 3I/Atlas wasn't sent to us. It wasn't aimed at us. It is not going to stick around, and it is not coming back. It was simply passing through, one anonymous traveler among what may be an enormous, largely invisible population of interstellar objects constantly drifting between the stars, the vast majority of which we will never detect, because they never happen to pass close enough or bright enough for our limited surveys to catch them. We got lucky. 3 times now, in less than a decade, we've gotten lucky. Oumuamua, tumbling and strange. Borisov, more comet-like but still foreign. And now 3I/Atlas, carrying possibly the oldest, most chemically alien composition of the 3. And each time, our tools have gotten sharper. When Oumuamua passed through in 2017, we barely had time to study it before it was gone, and we're still debating some of its basic properties. When Borisov arrived in 2019, we had slightly more warning and slightly better instruments. But 3I/Atlas arrived in an era when the James Webb Space Telescope was already operational, ready, and pointed at exactly the right patch of sky, alongside a global network of ground-based observatories that could triangulate its chemistry from multiple angles simultaneously: infrared spectroscopy from space, optical spectroscopy from the ground, radio observations from arrays like ALMA capable of hunting for individual molecules like methanol and hydrogen cyanide in the comet's tenuous coma. This is, without exaggeration, the most thoroughly studied interstellar object in human history, and it likely will remain so until whatever fourth visitor eventually follows it. Hopefully one will be even better prepared for. It's also worth remembering just how small this whole encounter really is, in physical terms. The nucleus of 3I/Atlas, the solid icy core underneath all that dramatic gas and dust, appears to be small. Estimates place its effective radius at well under 3 kilometers, and some measurements suggest an upper limit closer to 5 kilometers across at most. This is not a planet. It's not even a large asteroid. It is a modest chunk of ancient ice and rock, a few kilometers wide, quietly outgassing as it swings past the sun. And yet the story locked inside that small, unassuming body has forced scientists to reconsider assumptions about comet chemistry, galactic chemical evolution, and the diversity of planetary systems across the Milky Way. Size, in this case, tells you nothing about significance. There is a broader lesson buried in all of this, one that goes beyond the specific chemistry of carbon dioxide ratios and elusive metal signatures. For most of human history, everything we knew about the universe beyond our solar system came from starlight, photons that traveled, in some cases, for thousands or millions of years before reaching a telescope on Earth or in orbit. We learned to read those photons brilliantly. We can determine a star's temperature, its composition, its age, its motion, all from analyzing the light it emits. But starlight, however informative, is still just light. It's a signal, not a sample. 3I/Atlas is different. It is actual matter from another solar system, physically present in our own, close enough that we can watch it warm up in real time and measure the exact molecules boiling off its surface. That is a fundamentally different kind of data than anything astronomy typically works with. It's the difference between studying a photograph of a place and actually holding a rock picked up from its ground. For a few precious months, we had that rock, metaphorically speaking, passing directly through our own cosmic backyard, and every major observatory humanity possesses turned to look. And what we found, when we looked closely, was a chemistry that doesn't quite match anything we'd cataloged before. Too much carbon dioxide relative to water. Nickel glowing in the spectrum without its usual iron companion. Isotope ratios reassuringly familiar, yet an overall chemical fingerprint distinct enough to suggest an origin in a different galactic neighborhood entirely, possibly billions of years before our own sun ignited. It raises a genuinely humbling question, one worth sitting with long after the telescopes have moved on to their next target. How many other interstellar wanderers have already passed silently through our solar system, completely undetected, carrying their own frozen chemical secrets from other stars, other disks, other corners of the galaxy, simply because we didn't have a telescope pointed in the right direction at the right moment? Oumuamua, Borisov, and 3I/Atlas are not likely to be rare exceptions. Current models suggest interstellar objects should be passing through the solar system regularly. We're just now developing the tools sensitive enough and the survey coverage wide enough to actually catch them in the act. Every one of these visitors is a message with no return address and no way to ask follow-up questions. We get one pass, one brief window to point every instrument we have, gather every photon we can, and try to reconstruct, from spectral lines alone, the story of a place we will never see directly. A star system somewhere out among the 100 billion or so scattered across our galaxy, where the ice that makes up this comet first condensed out of a swirling disk of dust, long before Earth existed, possibly long before the Sun existed, following chemical rules that may have been subtly, fascinatingly different from our own. 3I/Atlas will not come back. Its trajectory carries it on a path that will eventually return it to the emptiness between the stars, this time forever, its brief and unlikely visit to our solar system reduced to nothing more than the data we managed to collect during its short stay near the Sun. In a sense, that's the entire story of interstellar objects in miniature. Brief encounters, permanent departures, and whatever we can manage to learn in between. What we managed to learn this time was substantial. We learned that comet chemistry, as varied as it already appeared within our own solar system, might vary far more dramatically across the galaxy than we assumed. We learned that objects can carry chemical fingerprints shaped not just by where they formed, but by billions of years of subsequent cosmic ray bombardment during interstellar transit, meaning some of what we're reading isn't a birth certificate so much as a weathered, radiation-scarred travel journal. We learned that isotopic ratios of something as fundamental as carbon appear to hold remarkably steady across vastly different environments, which tells us something reassuring about the underlying universality of stellar chemistry, even while surface compositions can diverge wildly. And we learned, once again, that nature is very good at surprising even our best prepared instruments and our most experienced scientists. There's a certain irony in calling something inanimate, a few kilometers of ice, dust, and frozen gas, a messenger. It has no intention. It isn't trying to tell us anything. It's simply following the laws of physics, the same laws that govern every rock, every star, every photon in the universe, indifferent to whether anyone happens to be watching. And yet, because we were watching, because we built the telescopes, trained the scientists, and pointed our instruments at exactly the right coordinates at exactly the right time, that indifferent, wandering chunk of ancient ice became, for a few months, one of the most informative objects in the sky. Not because it tried to speak to us, but because we finally learned how to listen. And maybe that's the real takeaway here, once you strip away the specific numbers and the spectral lines and the standard deviations. The universe is not obligated to explain itself to us. It doesn't send press releases. It doesn't leave convenient markers. Everything we know about places we will never visit, other stars, other planetary systems, other corners of the galaxy shaped by different chemistry and different histories, we have to earn one photon, one spectral line, one carefully measured ratio at a time. Sometimes that effort is rewarded with confirmation of what we already expected. And sometimes, like this time, it hands us a puzzle. A visitor from deep time and deep space, carrying a chemical signature unlike anything we'd cataloged before, forcing us to expand what we thought we knew about how comets, and the star systems that build them, can turn out. 3I/Atlas is already on its way out. By the time you're hearing this, it may already be beyond the reach of our best telescopes, fading back into the same interstellar darkness it emerged from, carrying with it whatever secrets we didn't manage to catch in time. But it leaves behind something that will outlast the observation window by decades. A body of data that scientists will be picking apart for years, refining models of comet formation, galactic chemical evolution, and the sheer diversity of planetary systems scattered across the Milky Way. And somewhere out there, right now, unnoticed, there is almost certainly a fourth interstellar visitor already inbound. Another fragment of some distant, long-gone protoplanetary disk, carrying its own peculiar chemistry, its own quiet answers to questions we haven't even thought to ask yet. We don't know when it will arrive. We don't know what it will look like, or what strange ratio of gases will show up in its coma when we finally get a spectrograph pointed at it. But if 3I/Atlas taught us anything, it's that when that next visitor does arrive, we'll be ready, telescopes primed, instruments calibrated, waiting for the universe to hand us the next unexpected detail. Because in the end, that's what this entire story really comes down to. Not a comet, not a chemical ratio, not even the tantalizing hint of a different galactic neighborhood billions of years in our past. Comes down to the fact that we noticed, out of the entire staggering vastness of the Milky Way, a small ancient traveler drifted close enough for us to catch, and for one brief moment, across observatories and continents and instruments built by thousands of people over decades, humanity looked up, took notice, and read the letter. We may never know exactly which star system 3I/Atlas came from. We may never know precisely how or why its ice ended up so disproportionately rich in carbon dioxide, or why its nickel arrived without its usual iron companion. Some of those answers may take years of further analysis to settle, and some may never be fully settled at all. But we know this, for the first time humanity held direct chemical evidence. Not a theory, not a simulation, but an actual physical sample that other corners of our galaxy can build worlds, and the icy leftovers of those worlds according to a chemistry all their own. And that, more than any single number or ratio, is the real discovery. Not that a comet looked weird, but that we finally have proof, sitting right there in the spectral lines, that the galaxy is far stranger, far older, and far more chemically diverse than the small, familiar neighborhood we call home. Somewhere out past the edge of what we can currently see, more of these ancient travelers are already on their way. And next time, we'll be watching,